Hello, my name is Hussein, and this is introduction. We are group 4 and this is our experiment 3. So let's start. First objective, to determine the coefficient of performance COP for vapor compression cooling system. Introduction, heat transfer process occurs in nature without any device. The reverse process can never happen by itself. The transfer of the heat from a low temperature region to a high temperature region needs a special device called refrigerators. Refrigerators are cycled devices while the fluids in the refrigerator is refrigerant which was used are 141p in this experiment. The refrigerator has a lower boiling point than the water. Theory and related applications. And this is our figure 2 schematic diagram of refrigeration system. Cool tank and hot tank. This is a conduit and evaporator. The vapor compression refrigerator cycle is a thermodynamic cycle to generate refrigerating effect with the use of compressor, condenser, expansion valve, and evaporator. It's a compression process. This process is basically a process where working fluid absorbs heat from the surrounding or low temperature space and reject heat to the atmosphere at higher temperature surface. This process requires work to be supplied to depict in figure 2. Theory and related applications. Refrigerant flow through the compressor which raises the pressure of the refrigerant. Next, the refrigerant flows through the condenser where it condenses from vapor form to liquid form. After the condenser, the refrigerant goes through the expansion valve where it experiences a pressure drop. Finally, the refrigerant goes to the evaporator. The refrigerant draws heat from the region that's to be cooled. The evaporated refrigerant goes back to the compressor to restart the cycle. Coefficient of performance (COP) can be calculated based on the following equation: COP, cooling effect divided by work net in.
Alright, so today I will present methodology for experiment 3. Okay, we need the apparatus. Number 1 is evaporator, 2 is condenser, 3 compressor, 4 valve, 5 main switch, 6 temperature indicator, and 7 temperature selector switch. Okay, we move to step by step. 1A, we have to identify the following components: evaporator, condensers, compressor, expansion valve, watt meter, water flows in and out, and the flow of fluid are 141b as depicted in figure 3. Number 2A, observe the thermometer for each position and do not blow out the vent valve. And for step B, for launch operations and record the readings, 1B, open the valve as illustrated in figure 4. Number 2B, open the water pipe and set the water flow rate to the evaporator as 25 gram per second and water flow rate to condenser as maximum. 3. Switch on the main switch. 4. Allow the cooling system to be stable approximately 10 minutes and record the parameters as listed in table 1. Then step 5. Repeat the experiment by changing the flow rate of water to condenser in between 35 to 40 gram per second. And the 6th step, repeat step 1 to 5 for 4 times. Alright, so for step C, terminating the operations. When an experiment is done, make sure the device is closed in accordance to this procedure. Number 1C is switch off the main switch. Number 2, turn off the water supply pipes after 1 minute. Number 3, close the valve to the shutdown position as depicted in figure 5 after 1 minute. That's all from me. I will pass to the next presenter.
Hello, I'm Shafi and I will be discuss about the result of this experiment. And for the formula that we use is heat transfer in the evaporator is Q equal to M delta H T2 minus T1. And for the second formula is heat transfer in condenser, Q equal to M delta H T4 minus T2. And the lastly for the formula is the coefficient of performance of refrigerator, COP, equal to modulus QL divided by QH minus QL. And this is the data for the vapor compression refrigerator. From the formula, we can get the rate of heat transfer at evaporator, KW, and rate of heat transfer at condenser. And lastly, the coefficient of performance, COP. The calculation will be discussed in the discussion part. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. So I want to present about discussion. So discussion for this slide, this calculation for rate of heat transfer at evaporator, which is calculated in kilowatt. Then we calculate the rate of heat transfer at condenser, also in kilowatt. So this is the result that we get for Q1, Q2, Q3, Q4 and Q5. Okay, the coefficient of performance is directly proportional to the rate of heat transfer in evaporator. It is also noted that the value of COP may be greater than unity, indicating that the amount of heat transfer from the refrigerated space may be greater than the work input. This is in contrast to the thermal efficiency, which can never be greater than 1. However, it is expected that some errors may occur during the experiment. Firstly, the temperature T1, T2, T3 and T4 do not have a stable fixed value. Thus, the observer may face difficulties in recording the value or might even record the wrong value for this temperature. Next, the insulator is not functioning at an optimal rate. Thus, heat is lost to the surroundings throughout the experiment, causing the efficiency of the motor to not be 100%, resulting in the values recorded were not to exactly real value that should be recorded. In addition, there were air bubbles present in the pipe, which will affect the flow rates that reduce the accuracy of the result obtained. Moreover, parallax error may occur when the observer was recording the value of T5, T6 and T7. First, the values were not stable upon recording. Secondly, the eye level of the observer might not be perpendicular to the measuring scale of thermometer. Okay. Next, the rate of heat transfer for the condenser QH have negative values, indicating that heat was released to the surrounding when the condenser was cooling the air. Flow rates in the condenser are directly proportional to the rate of heat transfer in the condenser. When the flow rate decreases, the heat transfer to surroundings also reduces. The pressure value of the compressor was positive values, while the pressure value of evaporator was negative values, because the compressor shows the absolute pressure while the evaporator shows the gauge pressure. Okay, we move to the graph. So this is the graph for absolute pressure against increasing temperature. So basically the graph is slightly linear. On the y-axis we have temperature, and on the x-axis we put absolute pressure in bar. Okay, next, graph of absolute pressure against decreasing temperature. So basically it's the same, linear. Okay, for the conclusion, based on the experiment has done, the function of the refrigeration cycle is to remove unwanted heat from one place and transfer it to another place in the closed system. From the result and the calculation, we obtain that the COP is offset 2, 3, 4 and 5 are almost the same, which is about 0.54 to 0.83, while for the set 1, the COP is in positive value, which is 0.51. It's because of the heat was released to surrounding when the condenser was cooling to the air, where T2 value is greater than T1. It might be because of result of the error, mostly because of the parallel error. In the experiment, there are some conclusions are made. The flow rates in the condenser is directly proportional to the rate of heat transfer in the condenser. The heat transfer rate is inversely proportional to the flow of water. That's all from me. Thank you.